You've probably heard of the irrational number e. It shows up everywhere, in growth, in money, in calculus, and even in nature itself. One of the ways we define e is through an infinite series, or more compactly, we can write that using summation notation. But today, let's do something cool with this number. Let's actually prove that e is irrational. We'll use something called a proof by contradiction, which means we assume the opposite, that e is rational. For this, we write e as a over b, where a and b are integers. This is essentially the proof by contradiction. We assume the opposite of what we're trying to prove and then show that this leads to some sort of absurdity. And if it does, that means e can't be rational. Pretty neat, right? Okay, here comes the clever part. We define a new number. Let's call it x. It's designed so that most of its parts will be whole numbers, and what's left will be a tiny leftover piece we can study. Basically, we're multiplying e by b factorial and then subtracting the first few terms of its series. Visually, imagine stretching out the series for e, then erasing the first few terms, leaving only the infinite tail. Remember our assumption that e equals a over b. We'll plug that in here, distribute b factorial like so, and simplify. You're going to notice that each term here is an integer, so x is an integer minus an integer, meaning x itself must be an integer. Next, instead of the rational e, let's substitute its true infinite series into that same equation. Here we see that both sums start at n equals 0. The second one stops at n equals b, but the first one goes on forever to infinity. That means that when you subtract everything from n equals 0 up to n equals b, what's left are only the tail terms starting from n equals b plus 1 onwards. This gives us a sum of b factorial over n factorial for all n greater than b. The key point here is that every term in this new sum is positive, which means our value of x must be greater than 0. Moving forward, let's see what happens if we take this part and expand it. We know that as n equals b plus 1, the expanded version of n factorial will always contain the complete expansion of b factorial within it, and thus, we can denote the expanded form as follows. Looking at this form, you can see that there's some cancellation going on. So, after pruning this factorial, there correctly remain n minus b number of terms in the denominator, and the smallest one of them is b plus 1. Now, we don't actually know the exact value of this denominator. It's got a bunch of terms like from n to all the way down to b plus 1. But what we do know is that every single one of those terms is at least as big as b plus 1. Now, what we can do is set a bound for this, a guaranteed inequality that helps us estimate its size. The whole denominator, this big product of n minus b numbers, has to be greater than or equal to b plus 1 raised to the power of n minus b. And if the denominator gets bigger, the whole fraction gets smaller. This trick helps us tame the factorial expression and move one step closer to showing that our mysterious number x is squeezed between 0 and 1. Now, we use this bound to estimate the infinite sum x and write it like so. We can substitute k here to make this look a little simpler. Rearranging the summation limit here and then plugging in k, we get this representation. This here is a geometric series. We can operate on it using the following formula, where a is the first term and r is the common ratio. Here, both a and r are equals to 1 over b plus 1, giving us the following expression. Everything cancels out beautifully to give us the condition we have been searching for. The sum equals 1 over b. And since b is a positive integer, that makes 1 over b less than 0. But remember, x was an integer, and the situation here shows that x is greater than 0 but less than 1. There is no integer between 0 and 1. That's the contradiction. This means our assumption was false, and therefore, E is irrational. By assuming E was rational, we ended up with an impossible result, a number that's somehow an integer, but still trapped between 0 and 1. That's the beauty of math. It doesn't just tell us what is true, it shows us why it must be true. Thanks for watching. If you enjoyed this, leave a like, and maybe next time we'll prove something even weirder.